Analysis of variance, we talked about a couple of this before. A lot of times in stats, we want to compare more than two groups. Doing the t-test and these z-score transformations is cool, but it's limited to two groups. And sometimes we want to go beyond that. We want to compare 3 groups or 4 groups or 15 groups, right? So we need something to deal with that. We talked about t-tests comparing mean differences between 2 groups. If we wanted to compare 3 or more groups, we could calculate a series of t-tests, but that's going to run into other issues, right? Let's say we're going to compare Black, white, Latinx, and other individuals. If we wanted to do it the t-test way, we'd have to do a bunch of paired comparisons. So it's going to be 6 different paired comparisons with these 4 groups if we want to exhaust all possible comparisons. But the problem with that is every t-test has a set alpha level, alpha of 0.05. If we run a t-test for one comparison, that's an alpha of 0.05. We run another t-test, that's another alpha of 0.05. So instead of actually finding significance, we're not controlling for the other groups that exist in the data, right? We're not examining true differences because we're deliberately excluding certain groups from the analysis. Essentially, we're biasing our results by limiting our sample that way, right? We're only looking at a subset and saying, does a difference exist? Well, how do we know if that difference is true if we're not also taking into account differences for other groups that exist in our data? If they didn't exist in our data, cool, that's fine. We don't have to make those comparisons. But because they do exist in our data, we're essentially contributing bias to the estimation process. So each comparison adds 0.05 alpha. So the maximum allowed probability that the null would be true would be 30% or 0.30. And that's not what we want. It's a weak test. We don't want that. We want standard tests. So the way we deal with that is we could just divide our alpha level by the number of t-tests that we want to do, right? So if we have to do 6 t-tests, we just say 0.05 divided by 6, and that's our new alpha level. But that's just a lot of work as well. Why not incorporate one test that does it behind the scenes? So that's exactly what we do. So we could do the t-test. This is what we'd end up doing. We're more likely to find a relationship when we break it up like this. And that's not what we want. We don't want to make it easier for us to find a relationship because type 1 error. Type 1 error has to do with whether or not the relationship we find is a true relationship. We're going to end up rejecting the null hypothesis when we probably shouldn't have. So we're saying, hey, there's a true relationship in the population when we shouldn't have. Reverse is a type 2 error where we don't reject the null hypothesis when we should have. You can think of lots of examples where you would want to reject the null hypothesis in favor of not, and the reverse. We're not terribly concerned at this juncture with the difference between type 1 and type 2 errors. Just know that if we run these t-tests, we inflate the likelihood that we're going to have a type 1 error. We're making it easier for us to reject, and we don't want to make it easier. We want to have confidence in what we're finding, confidence that there is a true population difference. So we need one overall or omnibus test to account for these adjustments. And that's the analysis of variance. So we've seen this already. I talked about this. So we have variation between groups and variation within. We have the mean of each of these groups, lower class, working, middle, and upper. We compare those between group differences, but we also compare within. How much does each person's raw score differ from that group's mean? I gave the example when we were comparing the gerontologists looking at method A and method B. Method A was obviously better. All the people's recall in method A was higher, right? Consistently in the low 80s. Everybody in method B had consistently in the high 70s, but they were very close together and they never overlapped. So that's important when we're looking for between group differences, right? Group 1 and group 2, is there a big difference or is there a small difference? We're trying to account for the difference between groups while also adjusting for differences within. So what we don't want to see is big spread of one group, big spread of another group, a lot of within group variation, but then the means of each group are really close, right? We don't want that. What we don't want to see is something like this. The mean of group 1, and then the mean of group 2, right? Where within group, this is a measure of within for group 2. This is a measure of within for group 1. That's a wide spread, right? And then between groups, we have small group variability, right? We don't want to see that. What we really want to see is the extreme case is something like this. We have right here and right here. We have mean of group 1, mean of group 2. Within group, there's little variability. All the scores are clustered together. Within this group, all the scores are clustered together. And then between groups, we have this huge variability between those groups. That would indicate that these two groups are extremely different from one another. Now we're just incorporating that same logic that we have from the t-test with more than two groups. So just like the t-test, we're looking at variation between groups over variation within groups. We're basically saying how much within group variance is the difference between these two groups, right? So we're basically breaking out group 1 is very close and together, group 2 is very close and way out here. We're saying how many of this group's steps does it take for us to get over to the mean of group 2? ANOVA does the same thing. We're looking at between over within. However, like the t-test, we calculated a observed t-value or a t-ratio of between within. Now we have an f-ratio. An f-ratio is the calculation for ANOVA. So we have a bunch of different ANOVAs, right? We have multivariate analysis of variance. We have factorial ANOVAs, which are independent and dependent variables. We have different kinds of factorial ANOVAs. We have repeated measures ANOVAs, but in this class, we're going to focus on mainly one-way ANOVA. You'll notice not only does the t-test form the foundation for ANOVA, but ANOVA becomes the foundation for regression, which is another way of running these comparisons. You don't have to always run it through an ANOVA format because some of the output that you're going to get from regression is an ANOVA summary. Keep that in mind. You don't need to know repeated measures ANOVA to do repeated measures kinds of things. You can do it in regression format. So variable type, same thing as t-test. However, we have 3 or more groups for our independent variable. So ANOVA, the assumptions for ANOVA: independence of observations, equal sample sizes, homogeneity of variance, and normality of distribution. Wow, these sound very familiar. Yes, they do. And that's because they're the exact same thing as we had for the t-test. Remember, this ANOVA test is just an extension of what we have in the t-test. Now we have this, the hypotheses for ANOVA. The null hypothesis is that all group means are equal. So instead of M1 equals M2 or mu1 equals mu2, it's mu1 equals mu2 equals mu3 equals mu4. Alternative hypothesis is just that all of these groups means are not equal in the population. Again, I will point out that while in the t-test, when we reject the null hypothesis, it means that the mean of group 1 is not equal to the mean of group 2. However, when you start throwing in mean differences for a third group and a fourth group and a fifth group, it becomes much more difficult to figure out where the mean difference is. You could have mean MPG for this type of car is 15 and another type is 14 and another type is 16, and then a final group is 25. And what we're doing here in this ANOVA formula is we're trying to find out how much variability is going on overall in the system. And we're trying to find out, is there enough variability in the system to say these groups are varying widely from one another overall? What that means is if one group is significantly different from the others, it can pull the test into significance, right? We can end up rejecting the null hypothesis if only one group is significantly different. So we need to go into this analysis thinking about what a significant F means, what rejecting the null means. It just means that one of these groups is significantly different from the others. It doesn't mean that all groups are different from the others, right? It'd be cool if you found that group 1 is way different than group 2 is way different than group 3 is way different than group 4. But the chances of you finding that are less likely than just one of these groups being significantly different. And that speaks to a larger need to investigate the data. You may find a significant overall test, but you're like, okay, are all the groups different from one another? Or is there just one group that's significantly different from everybody else? Is all these other groups, are they clustered together and one group is higher or lower than the others? We have to investigate. So you'd have to go and look at the data, look at the means for the groups, but you can also do what we call post-hoc tests, which is basically just rerunning the test, running different t-tests between these groups to say which groups are actually significantly different from the others, right? Or where that significant difference lies. So like I said, the ANOVA test is a measure of variation between and variation within. Much like the standard deviation calculation we did before, and some of the t-test calculations or z-score calculations, we have this thing called the sum of the squared deviations from the mean, which is the sum of squares, right? We know what the sum of squared deviations from the mean is. Everybody has a raw score. There's a mean for their group. You take up, you say, I'm going to subtract my score from the mean. Everybody gets a deviation score. But when we sum up all those deviation scores, because the mean is the center of gravity, they're going to sum to 0. So instead of just having it sum to 0, instead of taking the mean absolute error, the absolute value, what we do is we square that number. We square that number and it gives us different numbers. And that number, when we sum up all those squared numbers, it's called the sum of squares, sum of the squared deviations from the mean. That's an integral part of figuring out how much variability is going on. So we have between over within. We also have between over within. So here are the calculations, the stuff we'd walk through by hand, like we'd actually do hand calculations for this. So we have sum of squared deviations within. So if you look at this first line, SS within, it is the sum of the raw scores minus the mean of the group squared. So if we think about it, this first part is just the deviation score, or the part in parentheses is just a deviation score. You're saying person 1 has a score, the mean of their group, let's say they're in lower class, what's the mean income for lower class? Person 2, they have an income, what's the mean, again, from lower class? Each one is going to have a deviation score, right? And then we sum up all those deviations, it's going to give us an overall SS within. So each person will have this deviation score. If we come back here, it is basically saying person 1, what is the mean of the group? Person 2, what is the mean of your group? Person 3, what is the mean of your group? And then adding all of those up for that group. Doing the same for person 15, you're now in group 2, minus the mean of group 2, 16, 17, so on and so forth, until you've calculated all of the deviation scores. You've squared all those deviation scores, and then you sum them all up. And that gives you an overall metric of how much within variation is going on. So it's summing up the within variation for lower, for working, for middle, and for upper. Again, we're trying to get overall metrics of variation within. We do the same thing for variation between. Here we say, using that other graph, what is the mean of group minus the mean total? And mean total here is the mean of means, the mean of all group means. So we say the mean for lower class is 20,000. The mean of means is the mean of lower plus working plus middle plus upper middle. So what is the mean for all of those means? Because the mean of means is going to be the center of gravity, if you sum them up, it's going to be 0. So much like we did before, we're going to square those numbers, and then we adjust this calculation for the number of cases in each group. So we're going to say the number of cases in group 1, we adjust that number of cases in group 2, adjust that number of cases in group 3, number of cases in group 4, we adjust that number. We're taking variability between each of these groups. We're trying to come up with an overall system-wide metric of how much variability is going on between these groups. But we're saying we don't want to count these groups as equal, right? We don't want to treat them as equally contributing to the variability. What we're going to do is adjust or tamper down each group's variability from one another by the number of cases, right? We may have 4 people in group 1 and 50 people in group 2. Group 2 is going to have much more variability. Why? Well, we have a lot more cases. So we need to adjust for how much they can contribute to the overall between sum of squares metric. That's what this is doing. And then we have sum of squares total, which is just between plus within. So again, you may have walked through this as an undergrad, actually writing these out and calculating sum of squares before. I'm going to rely on your domain knowledge for that. I won't have you do that. Within, it's the mean difference in scores within a sample, and then sums up all of them. Another way of thinking about it is the amount of unexplained variance by the group or between groups. So the group's deviation from each other group, we're trying to blame it on the groups. If group 1 has a mean of $50,000 and group 2 has a mean of $60,000, we're saying because of the groupings, that's what accounts for the differences. But those means are based on actual values, actual scores, actual raw scores. So when we calculate within groups, we're saying whatever is going on within the lower class group, we can't say that it's because of their grouping, because everybody's coming from the same group. We call that unexplained variance. because we don't know what's accounting for somebody's raw score overall and the spread to account for the mean income for that group. So unexplained because we don't know what contributes to each person's score. But when we compare the groups, we're saying the reason is the grouping. And then between groups, it's just the mean difference between all of the groups. And then total variation is just a summation of between and within. Here's an actual calculation for how to get the total sum of squares. Each person's raw score minus the mean total. So remember, we have raw scores minus the mean of the group. We also have means minus the mean total, or the mean of means. But we can take a sum of squares total, which is each person's raw score minus the mean of means. So we calculated sum of squares between, sum of squares within, right? With increasing numbers of cases, we're adding variability to the equation. So the sum of squares increases as sample size increases. So this number is going to be huge. So what we need to do is adjust for sample size. We need to adjust for the number of cases that we're putting in. Like if we just keep throwing cases in, no matter how many groups we have, we're squaring those numbers. So if somebody has a deviation score of 1, you square that number, it's 1. If they have a deviation score of 2, we square that, it's 4. If they have a deviation score of 10, we square it, it's 100, right? So the logic here is as sample size increases, because we're trying to adjust for those deviation scores and we square them to adjust for them, this sum of squares number is just going to be outlandish. So with more cases, it's just going to grow and grow and grow no matter what. So to fix this, we need to adjust the sum of squares by controlling for the number of cases. However, it's not the number of cases that we're controlling for, but degrees of freedom. The number of cases within each calculation that are free to vary. Remember, because we don't have population information, we're relying on our sample. If we calculate a mean for a sample, we can work backwards and we can have any possible values except for the last one. So that means that that last one's fixed based on all of the cases, right? So instead of adjusting for sample size, what we'll do is adjust by degrees of freedom. How many bits of information can go into there varying freely? When we adjust, meaning divide by this degrees of freedom, we're going to have a new calculation called mean square. So this mean square is now calculated this way. We can have mean square between, which is sum of squares between over degrees of freedom between, and mean squares within divided by degrees of freedom within. And now you're saying, Burl, wait, you just said divide by degrees of freedom, and now you're saying degrees of freedom between and degrees of freedom within. And that's because there are 2 different degrees of freedom calculations based on what means we're comparing. Again, everything's based on how we're estimating some parameter from a statistic, and everything's based around the mean here. So we have to figure out what are we comparing when we're comparing these means, right? How many bits of information go into comparing differences of means? When we're comparing groups, we're saying, how does the mean of one group compare to the mean of other groups? Or rather, how does the mean for one group compare to the mean overall, the mean of means? If you took the mean of all possible means, you have mean of 5, mean of 5, mean of 10, mean of 10. So you end up with 7.5. What I could tell you is if we have a mean of 7.5, you could let all those numbers, 5, 5, 10, and 10, vary randomly. But if you have 3 of those numbers, it automatically predicts what the last number is going to be because you let those 3 vary out of those 4. So much like we did with our other calculations, degrees of freedom is centered around this idea of n minus 1. So here we have degrees of freedom between and degrees of freedom within. Degrees of freedom between is the number of groups minus 1. If we have 4 groups, we're going to need 3 degrees of freedom, meaning 3 cases are free to vary, which implies that the last one's going to be fixed. You get the mean of means by implying that the last one's going to be fixed. The same thing can be said for degrees of freedom within. Wait, it says n total minus k. Here I say k is the number of groups. So let's assume we're working from this example of lower class, working class, middle class, upper class. So we have 4 groups. Degrees of freedom here is still going to be 3, right? 4 groups minus 1 is 3. Let's say we have 100 people equally split between the groups 25 in lower class, 25 in middle class, 25 in working class, 25 in upper class. Here I say degrees of freedom within is n total minus k. So we have n total, which is again, how much? 100. K is 4. So degrees of freedom within would be 96, right? Now let's think about it. Why does this make sense? Well, if we know the same logic for every test that we're running, n minus 1, we see that clearly with this degrees of freedom within or between. K minus 1 is similar to n minus 1. With n, what we're saying is 100 cases minus 4. It's the same thing as saying 25 minus 1, 25 minus 1, 25 minus 1, 25 minus 1, which is n minus 1 for each group. So we're just summing n minus 1 for each group, which is equal to n total minus k. That's all we're doing. I could rewrite this as n of group 1 minus 1, plus n of group 2 minus 1, plus n of group 3 minus 1, plus n of group 4 minus 1. And it's the same thing. Just like for the t-test, we said n of group 1 plus n of group 2 minus 2. We could say n of group 1 plus n of group 2 plus n of group 3 plus n of group 4 minus 4. It's all going to be the same. N minus 1, that's what's important. So now we've adjusted our sum of squares by degrees of freedom for both between and within. So we have ms between and ms within, and we can take that information, and now because we've adjusted for these outlandish huge sum of squares numbers, we can now create a measure of variation between or within, which is the F statistic. The F statistic is ms between over ms within, which is also ss between over df between, all over ss within over df within. Everything in the numerator is an adjusted metric for how much variability is going on between groups, overall variability going on within groups. So if we see a big numerator and a small denominator, what that means is there's only a little bit of variability going on within each of these groups. So there's not big spread, they're small homogeneous groups. If we see a big numerator on top of that, we also know that they're distant from one another. So they're small in terms of their spread, but they're distant from one another. That's ideally what we want to see. And if we see something like that, what that indicates to us is most of the relationship that we're seeing between these two variables can be accounted for by someone's group placement, or alternatively, the grouping variable is what's explaining these mean differences. If all these scores are clustering really tightly around the group mean, and the groups are distant from one another, most of the variation in the outcome is going to be explained by that grouping. Now, if we had a situation where all of the variation was happening within and nothing between, we'd have a low numerator, high denominator. This F ratio would be small, but would indicate significant overlap. These groups are really spread out in terms of their variability within, but then they overlap with one another too. So being part of one group versus another isn't indicative of one's mean because there's just so much overlap. So essentially what we want to see, like we saw with the t-test, we want to see a high or large F value. With the t-test, we wanted something over 1.96, but we know that the curves differ, but we want those high numbers. Same thing for ANOVA. We want a high number. We want to beat whatever critical value that exists. Just like the t-test, the F test or ANOVA test has multiple curves. The t-tests have multiple curves for their distribution. F distribution has multiple curves as well. And each is based on sample size, or rather degrees of freedom. Here we have an example of what these curves look like. This first curve with degrees of freedom 1, so degrees of freedom between of 1, degrees of freedom within of 1. This second one with degrees of freedom of 5, this blue one, 5 and degrees of freedom within of 4. It looks more like a Poisson distribution. As the number of groups and the number of cases increases, number of groups is between groups, the number of cases within minus the number of groups. So we see here this has more cases across all of them, but also more groups. This brown one is sort of peeking out from everything else, right? What that indicates to us is as we increase cases, but also the number of groups, we get closer and closer to what would look more normal. I don't think the F distribution actually gets to normal distribution because it's not spread across similar ranges. It's positive values only. But with increasing numbers of cases, it does begin to look more normal. This part of the curve starts pulling more this way, in this direction. Hypothesis testing, we're doing the same thing that we were doing with t-test. We're trying to find if the variation between all of these group means is extremely different from what is expected by the null. The null, like the t-test said, there's no mean difference between these two groups. The null for ANOVA is there's no mean difference between these 3 or 4 or 5 or 15 groups. So now we say, okay, we did find a difference. If we did find a difference, how big or how extreme is that difference from what is expected by the null? Recall the t-test. If T obtained is larger than T critical, then the difference between these groups is so extreme that we can't blame it on chance or sampling. Therefore, it's so extreme that it's in the rejection region. We reject the null. P is less than alpha, usually 0.05. And then we find a statistically significant difference. Same thing exists for F. So just replace T with F. If our F obtained or F calculated is greater than our F critical, because we're using that same logic for the F test for ANOVA, our F obtained is going to be larger than our critical. That means our differences between these groups, or overall differences between all of these groups, is so extreme that we can't blame it on sampling error. So the null is probably not true. That means our obtained is now in the rejection region. We've crossed that finish line. We're now in the rejection region. We can reject the null. P is going to be less than whatever our selected alpha is. And there's a statistically significant difference between these groups. We don't know which group or which groups are significantly different from one another, but what we find is overall within the system, there is a statistically significant difference that exists there. You could have the case where you have 15 groups you're comparing, all of them are clustered near one another, and you have one group that's way out there and significantly different from everybody else. And that could still be a statistically significant difference in the system. I will note that because we squared these differences, and if you remember when we were calculating z-scores and standard deviations and things like that, we readjusted. Once we squared these differences, we'd take the square root of those numbers. We did not do that here, but we did adjust for the number of cases. So we brought those numbers back down. We just didn't put them in their original units. So that is to say that because we squared these differences, we only have positive values. So the F test is only positive values. So we have multiple distributions, just like the t-test. Like the t-test, we had a degrees of freedom and an alpha level. But for the F test, we have 2 degrees of freedom and an alpha. So we can use that information to figure out what is our F critical value. And we can compare our F obtained to that critical value. What we're trying to see is our calculated or obtained value, is it greater than our critical value? And if it is, then we can reject, it's in the rejection region, all of that same stuff. So we need to figure out what is our critical value. So we refer to a table. Have another table here. As we saw in slide number 30, if you want to go back to it, the distribution started at 0 and they continued on. So to figure out what our critical value is, we use this table, we use our alpha and our degrees of freedom between and degrees of freedom within, and see if our obtained is greater. So I'm going to open this up. So we have degrees of freedom numerator, degrees of freedom denominator, degrees of freedom between, and degrees of freedom within. We can use this information. So this is an alpha of 0.025. I don't need that. We have an alpha of 0.05, so that's good. So again, this is not a two-tailed test. This is a one-tailed test, and that's because it's all positive values. So let's say we had a degrees of freedom between of 20 and degrees of freedom within of 20 as well, 2.12. We would need to beat that number because that is our critical value. You just compare like you did for the t-test. If our obtained F is larger than the critical, then we know our obtained F is significant, at least at the alpha level. At the P is either 0.05 or 0.025 or 0.01 level. Once we do that, we report it just like we did for the t-test. Report the test, whether we reject or fail to reject, the variables used, the degrees of freedom, and the actual reporting of the test. So using a one-way ANOVA, I either reject or fail to reject the null hypothesis that there's no mean difference in the dependent variable across groups of the independent variable. And that's because we're not comparing 2 groups, we're comparing a bunch of different groups. So we don't want to say the mean of this group and the mean of this group and the mean of this group and the mean of this group. It's easier just to say there's no mean difference in whatever the outcome variable is across these various groups of the independent variable, comma, in the population, right? Because we're trying to infer to the population. Remember, we're estimating these parameters based on statistics. In the population, comma, F of degrees of freedom between, comma, degrees of freedom within, equals some F obtained value, comma, P is either greater than or less than or equal to 0.05. An example, does monthly income vary by race? So we're looking at the outcome of income. So mean income by one group compared to another group, compared to another group, compared to another group. And we say, does dollars per month vary by race? Is there a significant difference between mean monthly income for people of different racial categories? So we're comparing Black, White, Latinx, and other. Here's the monthly income breakdown for a bunch of different groups. So these are data I created. There is some variability, right? How do we know? Well, everybody has different scores. So we have 4 groups. This is how we typically do it with my classes. We create a table like this, calculate the group mean, the grand mean, which is the mean of means or the mean total. And we use this information to calculate each one of these: SS within, SS between, and SS total. Within the black category, we have 3670, then 3132, 3798, so on and so forth. So we have 5 people within each group. So we know at least we've met the assumption of equal sample sizes, so that's good. We have each group mean. We see that one of these groups is a lot higher than the others, right? At least looking descriptively. We see that the white category tends to have higher mean monthly incomes than Latinx or Black or other. And then we can use this information to calculate these things. So we use that same information. Here's that table again. And we use this to plug it into the formula. So within group sum of squares is the Black value minus the Black group mean squared. So this person is 3670 minus the group mean. So that's a deviation score, and we square it. Second person is 3132 minus 3546 squared, and it's that. So these are just each person gets a deviation score squared. Same for the white group, Latinx, other. You see how this can take forever? This is just 20 people. That's way too small a sample for anything. Imagine if you had 100 or 200 or 500, right? It'd be forever. So we have a sum of squares within, right? We just add all of those deviation scores up. Sum of squares between is just Black group mean minus the grand mean. So 3546 minus 3932 squared, and that's that. White mean minus the grand mean, that and that. We sum all of those up, and it's this huge number, 7,325,888. These are huge numbers, right? We take those numbers. SS between is 7 million. SS within is 9 million. What we're looking for is a lot more variability between and a lot less variability within, right? That would indicate to us that there's much more variability between groups, explaining the reason for the outcome, differences in means. Groups are what's explained. What we're looking for is that groups are explaining the differences in means. Here we see that might not be the case. We see 9 million within, so much more variability within than between. However, remember, these are huge numbers because we haven't adjusted for the number of cases, or rather degrees of freedom. So we adjust and make them into mean square calculations. Degrees of freedom between is 3, right? We have 4 groups, minus 1 is 3. We have 20 people, minus 4 groups is 16, is degrees of freedom within. So now we have 3, which is going to be the denominator for our calculation of mean square between. Degrees of freedom within, which will be the denominator for mean square within. We use that, we plug it in, and now we see 7 million over 3 is 2.4 million. 9 million over 16 is 604,000. So we have mean square between and mean square within. So it's going to be 2 million over 604,000, which gives us our F statistic of 4.04. I will make a side note. Here we're calling it between and within. An older school way of talking about it is, instead of saying within, when we run it in R, it says error. Remember, variability within is saying what else explains what's going on. There's a lot of stuff out there in the ether could explain people's scores, right? So it's unexplained or error variance. Now that's going to be our F obtained value of 4.043. What do we do with that F obtained value now? We look in the appendix, it tells us our critical value. We say, okay, is it greater than our critical value or less than? So we have our 2 degrees of freedom value, our F obtained, and we can determine whether our F, representing the size of the mean differences between groups, is significant. So we say, we take that information, we compare it to the appendix value. The critical value, when we look in the back of the book, there are these tables in the back of the book. We can look at those values and we'll see that our critical value for degrees of freedom between of 3 and within of 16 and an alpha level of 0.05, they have a critical value of 3.24. So we have an obtained of 4, a critical of 3.24. What does that mean? Without moving forward, what does that mean? If our obtained is 4, our critical is 3.2. Where are we? What region are we in? The rejection region. Is this difference statistically significant or not? Yes, because we're in that rejection region, right? So statistically significant. And what is P? Is it exactly 0.05? No, right? Because we're in the rejection region, that means everything at 3.24, that critical value, everything beyond is 0.05. We said we're beyond that, we're at 4. So everything beyond 4 is going to be less than 0.05, right? So all of those steps tell us whether or not we're significant or we're in the rejection region. All of those steps tell us the same thing, right? We passed that finish line, that means we're in the rejection region, meaning we reject, meaning P is going to be less than whatever our alpha is. And that alpha is 0.05, so P is going to be less than 0.05 at that point, right? Meaning we have a statistically significant difference in this overall test. Even without going to the next slides, we know 4.04 is greater than 3.24. We know we have a significant difference. Because F obtained is greater than critical, it means the mean differences between groups is so extreme enough to fall in the rejection region. Therefore, F obtained is in the rejection region. Therefore, we reject the null hypothesis. Therefore, P is less than 0.05 or our alpha. And we have a statistically significant difference between these group means. This also means that, more specifically, that at least one of our group means is significantly different from others. It doesn't mean that all of them are different from one another. It means that at least one of them is significantly different from others. Now, we want to write this out. Using a one-way ANOVA, I reject the null hypothesis that there's no mean difference in income across racial categories, comma, in the population. F of 3 and 16 equals 4.043, so our F obtained value, comma, P is less than 0.05. You can also say P is less than or equal to 0.05. So here, before we get to understanding what correlation is, I will mention that there's a correlation coefficient called R that we square that tells us how much variance in the outcome is explained by the predictor variable. Just keep this in mind for when we move down the line. We could figure out how much of the outcome or changes and values of the outcome is explained by changes in the independent variable. So how much of income is explained by group membership or racial categories. And we can do this with this calculation for eta squared. So I'll quickly move into this or through this. Well, we can come back to this calculation for the strength magnitude of the effect after we've done correlation. But please keep this calculation in your memory so we can come back and use it for analysis in the future. ANOVA is an overall test, omnibus meaning overall. It's an overall test of differences. So when we find a significant F test, what it means is that at least one of the groups is significantly different from the others. It doesn't mean that they're all different. It means that one of them, or at least one of them, is different. The next step is figuring out where that difference is. That means investigating the data a little bit more, looking at the means a little bit more, or we can do some post-hoc comparisons to figure out where those differences are and see if they're actually significant. The first step is to figure out if we find a significant omnibus test. If we don't find a significant difference overall, it's probably not wise to go cherry picking and see if these groups differ from one another. So the first step is to get an overall omnibus significant F, and then we can proceed. After we find a significant F test, right, which we did in our case, looking at income differences by racial categories, the next step is to identify which group is different from the others, or which group means are different from the others. So we can do that by looking at the means, or more appropriately, we can plot those means. So we actually do that, and we see this. What we're plotting here is the mean income. So remember, income is what dollar amount people are bringing in per month. And we have these groups, these racial categories with 5 people in each of them. And we see the mean for Black is here, Latinx is here, other here, white is way up here. Here's the 95% confidence interval around those means. So this is where 95% of the cases would fall. And what we see is the Latinx group tends to be lowest, and the white group tends to be highest. We see that there's more spread for the white group, less spread or more homogeneity for the Black group. So if I were looking at these data, I would say it's probably the case that when comparing Black and Latinx, those are about the same. they have about the same because they're like the spread of these, the spread of Latinx encompasses the spread of Black. So they're about the same. Similar things can be said for others compared to Blacks. The means are about the same. They're both like what, 3,500 and about 3,800. Right? When we compare Black to white, they seem extremely different. 4,800 maybe, and then 3,500, right? This and this seem completely different. Latinx and white seem extremely different. Other and white, they seem different. I don't know if it's extremely different, but they do seem different. So what does that mean? Well, we see differences. What we can do after examining these differences is see, are these differences between these groups significant? Or rather, can we figure out which groups of these are significantly different from other groups? So beyond plotting the means, we can do some post-hoc tests, multiple comparison procedures. So much like we said before, we can run a series of t-tests to see if these differences exist, but controlling for omnibus or overall alpha levels by using the ANOVA. So this is why this idea of conducting t-tests, while it is important, we use it as a check, a post-hoc check after the analysis check, rather than the actual analysis, right? So the omnibus test is the actual analysis. The post-hoc comparisons are going to be t-tests similar to what we wanted to do, but they're just like following up. So we can run a series of two group comparisons, but again, we still have that problem of type 1 error, right? Saying that a difference does exist when one doesn't. Well, how do we control for that? Well, we tamper down the family-wise error rate. The omnibus F test or ANOVA test already has built into it a family-wise error rate. It adjusts alpha based on how many comparisons are going on. When we're doing post-hoc tests, we have to do it ourselves. So we adjust, we figure out how many comparisons we want to do and figure out what the overall error rate is going to be. So if we had 3 groups, that's going to be 3 comparisons. We're going to have a certain chance of having a likelihood of error. 4 groups, we saw this before, we have 6 comparisons, there's going to be 26% chance of error, right? As we increase the number of groups, it increases the number of comparisons. It also increases the overall error that we're contributing to this problem. ANOVA, again, keeps family-wise error down. So again, we have to adjust. If we want to run these post-hoc tests, which are just t-tests, we have to adjust how much error is going on, right? We don't want 50% chance of error. We don't want 40% chance of error. We want the error to be 0.05. So how do we do that? We use Bonferroni's adjusted alpha by dividing it by the number of comparisons that we're doing. How many comparisons are you doing? Just divide your alpha by that. Super intuitive. So what we can do is run a series of t-tests using a new alpha level. So instead of 0.05, if we're doing 6 comparisons, we just say alpha of 0.05 divided by 6. Now that's going to be our new alpha. And we say it's only a significant difference if we are smaller than that new alpha. But instead of doing all of that, there are again programs and packages built to do this kind of work. And especially in R, we have these post-hoc tests that incorporate Bonferroni's alpha adjustment into these post-hoc t-test comparisons. A bunch of different tests. We have Tukey's HSD, we have Fisher's LSD, Chaffee's, and Dunnett's. And all of them incorporate Bonferroni's alpha adjustment. But the most common, I think the most used is the HSD. For us, we're going to go with Tukey's HSD as our post-hoc comparison. And what we can do is run the Tukey's HSD test to tell us where the significant differences lie. So when you do that, the Tukey's test will tell you the group that you're comparing, the actual value difference, and an adjusted p-value. So it calculates a t-test between, for example, it calculates a difference between Latinx income and Black income, adjusts the p-value or the alpha level, and then readjusts it back to put it back in alpha level 0.05 terms. So here, we're looking for a significance that's less than, or p that is less than 0.05. Here, we see the comparison between Latinx and Black. Latinx and Black, the p-value is 0.96. So again, not less than 0.05, meaning that Latinx and Black is probably not a significant difference. That's what that means. It's only a difference of $200 per month. P again is the likelihood that the null is true in that case, right? So there's a 96% chance that the null is true, that Latinx and Black are the same mean. So basically the null is true. Same here, when you compare other and Black, $419, $420 difference, 83% chance that the null is true. So other and black, these are basically saying that there's not much of a difference between other and black. White and black, same thing. White and black, no real difference, but there's only a 6% chance that the null is true. So it's almost reaching our critical value. Other and Latinx, again, similar. What we find here is that the only difference that exists, the only t-test difference that exists, a significant difference that exists, is between white and Latinx. There's a difference amount of $1,500 a month, and that difference is at 0.02. So the likelihood that the null is true is about 2% chance, right? The 2.5% chance that the null is true. P is less than 0.05, so we know that when we look closer into these data, while we do find a significant overall F, significant overall ANOVA test, the true difference, or the mean comparison that's holding that difference, is the comparison between white individuals and Latinx individuals, such that white individuals are making significantly more than Latinx individuals. We'll come back here. Our packages are loaded. Here in this next line, I say you can run the empty cars mission. We know what the empty cars looks like. Cool, we don't need to see it all the time. I'll do here is I'm creating an object, that way I can run the stats on it. So data one is now empty cars. Now here I'm looking for independence of observations, meaning I examine data collection strategy, equal sample sizes, homogeneity, variance, and normality. So independence of observations, I said I examined the data collection. None of these cars were tied to one another, so independence of observations assumption has been met. Good, so we met that. Equal sample sizes and homogeneity of variance, both of those you can check by using the descriptive statistics or univariate statistics function. So we describe by group. Here we're looking at the relationship between the number of cylinders in a car and the MPG. So we're going to say run the univariate stats or descriptive stats for MPG broken out by cylinder. So we're going to do that here. We see 4-cylinder cars, 6-cylinder cars, 8-cylinder cars. We're looking for equal sample sizes. 11, 7, and 14 are the sample sizes. I don't think they're that equal. I would have liked to see more equality, but for the purpose of the example, I'll say, okay, we've met that assumption. I think in the assignment, I think the groups are a little bit more equal, so we don't have to worry about that. It's hard to tell here because there's such small sample sizes, but at least for this purpose, we'll say equal sample sizes has been met. So we met independence, equal sample sizes. Now we're looking for a standard deviation that's not 3 times more than the other. And we see here, this standard deviation is 4.5. Here it's 1.45, so that's about 3. So it's right on the cusp. This other one's 2.5 in the middle. So for us, we're going to say, okay, it's about 3 to 1 is the maximum. So we've met that assumption. Good. So we've met those 3 assumptions. The next one is to look at normality. How do we visualize normality? By using histograms, box plots, and QQ plots. Here's the histograms. We see some negative scores in terms of kurtosis. I think that's platykurtic for all of these. This first one's highly skewed. So not the best. I wouldn't say these are particularly normal, but let's see what we see from other kinds of graphs. Let's look at the box plot. Box plot indicates most of the scores are between the extremes, like the 50 percentile. Between the extremes, we have the median falling about the middle in each of them. We have one outlier here, but that was sort of expected with these data. So given this, I think that they're kind of normal. Not the prettiest, but they're kind of normal. QQ plots, Most of the cases center around normality for each of these. The most normal happens for 6-cylinder cars. Wow, look at this. This is bad. These data and these data here, we see like there is a discernible pattern. There's like an S shape going on here where it's down here and up there, right? Maybe not as discernible as like a fanning out, like a trumpet, the bell of a trumpet or a trombone. But we do see it's lower than expected on the low end and higher than expected on the high end. So I wouldn't like to see that. Same here, lower on the high end, higher on the low end. If I saw this in real life, I would be like, okay, we probably shouldn't be making these comparisons. But again, for the purpose of an example, we'll say it's normal enough. I do want you to make that clear when you're doing the assignment, whether it's normal enough or if it's actually normal or if you violate some of those assumptions. Here, I would like, if I were being honest, we're violating some assumptions, right? Especially with this 8-cylinder group. All right, the next step is to run the ANOVA. So what we'll see here is a bunch of different information. And it's going to say data 1 cylinder. And if you remember, cylinder happens to be our grouping variable, right? We're looking at mean MPG broken out by groups, cylinder groups. So if it's our grouping variable, it's our between group indicator, right? So we're going to have this first row is going to say a name of a variable, but it's going to be our between groups information. Where it says residuals, that's going to indicate our within group. So I said that sometimes in statistical programs or old school statistical software or old school statisticians, they say between and within, but sometimes they say between and error. Another way of saying that is between and residual, right? Here's part of the reason why I'm pointing this out is because I'm just going to rewrite this function so it actually says between and within, so we don't have any complications. But this first row indicates the between group information up till here. If it would let me highlight the right stuff. So this is between, residuals represents within. So if we wanted to look at this, we'd say between groups, within groups, here's degrees of freedom, here's sum of squares, here's mean square, right? So we have 1 DF between, 30 DF within. Sum of squares between is 817. Sum of squares within is 308. Mean square between is 817. Again, why is that? Well, we have 1 degree of freedom between. Degree of freedom within is 30, so sum of squares over 30 is 10.3. And we say mean square between over mean square within, and that equals our F value of 79.56. So F value here is our F obtained. And what we're doing is comparing our F obtained value to our F critical. Now, I could ask you to go to a table and compare that to a critical value table or a critical value in the table, but I don't do that. Why? Well, the program is doing it itself. So what we have here in this final column is the probability that your F value is greater than a critical F value, or rather, you can call this column the P value. So our P value here is 0.000000000061. Let's say it differently here. Does yours say 6.11 E negative 10? Why does it say that? Well, back a while ago, I turned off scientific notation. So mine says it a little bit differently. I think it's 1. There we go. So let's clear this. I'm gonna run this again. So 6.11 e -10 is basically 6.11 times 10 to the -10. So it's 6.11 times 10 to the -10 power. 10 to the -10 power is 10 to the -1 is just 0.1. 10 to the -2 is that. 10 to the -3 is 10 to the -4, 10 to the -5, -6, -7, -8, -9, -10. So instead of 6.11 times 10 to the -10, it's translated as 0.00000000611. That is our p-value. So is that less than 0.05? A lot less than 0.05. So we can work backwards. We can say, okay, if it's less than 0.05, that means it's past our critical value, right? That means it's in the rejection region. That means we can reject the null hypothesis. That means there is a statistically significant difference between these groups, right? Between mean and PG for cylinders. Another way of visualizing that is instead of figuring out what that p-value is and working backwards, you have significance codes. It's a nice little shorthand. It provides significance codes for us to tell us if we've met significance, if we found a significant difference. If you find 1 star, that means you at least met the significance at the 0.05 level. So if you find 1 star, that means p is less than 0.05. If you find 2 stars, that means that p is less than 0.01. 3 stars, p is less than 0.001, right? And here we find that it's much, much less than 0.001. So anytime you see a star, it's going to indicate that it's significant at the 0.05 level or less, right? So we can use this information to say, using a one-way ANOVA, I reject the null hypothesis that there's no mean difference between miles per gallon in cars with different cylinders, comma, in the population F of 1 and 30, right? 1 from this result and 30 from this result, equals 79.56. 79.56. P is going to be less than or equal to 0.05. And why is that? Because it's much less than 0.05. All right. We report it that way. Then we want to see which means differ. You can just plot the means using this function. I have it in here. Yeah. Plot means. So you can see there's not even overlap between 4-cylinder cars and 6-cylinder cars, or 4-cylinder cars and 8-cylinder cars, or even 6-cylinder cars and 8-cylinder cars, right? It may be that all of these are significantly different from one another. So the overall significance that we found is not just one group significantly different than the other, but all of them significantly different from each other. Well, how do we test that? We test that using this function here. To figure out the difference, you run this, and you have this. It's saying a 2-key multiple comparisons of means with a family-wide 95% family-wise confidence interval. So what you're going to see in this result is comparing. So if you can see my table down here, let me zoom in a little bit. You're comparing 6-cylinder cars to 4-cylinder cars. The difference is -6 points, -7 points. It's giving us a 95% confidence interval, so the lower and the upper. And then your adjusted p-value. So you're comparing this to 0.05. And you want to, if there's a true difference, then it should be less than 0.05. We say when we compare 6-cylinder to 4-cylinder cars, they are significantly different from one another. 6-cylinder cars are have significantly less MPG than 4-cylinder cars. 8-cylinder cars compared to 4-cylinder cars, whoa, P is 0.000000000. It's never going to be exactly 0, but it's so small that it's going to take a bunch of different zeros to get there. So 8-cylinder and 4-cylinder cars are completely different from one another, right? So these two are significantly different. So we find a significant difference between these two, significant difference between these two. And then finally, when we compare 6-cylinder to 8-cylinder cars, we also find that these two are significantly different from one another. 0.01 is less than 0.05. So it's not just that one group differed from all the others, it's that every one and every comparison differed significantly. And that's why overall we find a hugely significantly different relationship.